I will meet someone. Here. Wait, let's see. I think I need to allow. No. It worked before. Okay. Okay. That's perfect.
There we go.
Okay, here we go. Okay, many thanks. You made it to the last talk, and I promise I don't show any formulas, only pictures. I'm a surface geometer, so I study surfaces in 3 space, and the most fascinating part of it is that I can show pictures rather than formulas and proofs. So let's look at applications since we are at PIMSA here. The first one shows a human brain, a little bit more prettier than you might expect. And how you apply surface theory to the human brain is by using conformal mapping. So you have a chart, basically a map of your brain, which region is which. And you do it conformally so that you don't miss, as surgeon, you don't miss the areas. The second one I will talk about later a little bit more are minimal surfaces. So the first one here, maybe you see my mouse. Yes. Are soap bubbles with boundaries. So you would dig that boundary into soap film, right? And that's what you observe. The other one is observed in nature in butterfly wings. And actually this guy right here is discovered by Alan Shern, not Rick Shern, in the 70s, who is a physicist working in NASA. And he discovered the minimal surface first, and then the biologists discovered that these structures are used in butterfly wings and also in crystals. So material scientists are really much interested in these triply periodic minimal surfaces in R3 because they give somehow good materials and have good properties. Okay, and one of the features you want to see is that if you have a little film building those structures, meaning the upper and lower layers are rather constant mean curvature surfaces with some liquid in between, maybe. What kind of, how to describe that better than just an infinitely thin surface. Now, you can also use surface theory in architecture, in particular free-form design. And here you can see these curves here, okay, are transformations of each other. And the idea, of course, is since you want to have glass in between, which should not be bent, right, you need good theory that guarantees that the 4 points of your lattice basically are on a plane, meaning that cross ratio of these 4 points should be real. And if you're interested in computer games, and I was very unsuccessful to promote computer games here in China among my students, so nobody actually plays. That's not the case with my kids, but okay. If you're interested in that, surface theory also helps you to do 3D computer games. And if you are an art director and you really want to save money, okay, what you do is you start with a shape with some formulas here on it, and then you maybe don't like it as much and you want to change it a little to the right-hand side, for example. You want a good way to change it without recomputing everything. And in a way that doesn't stretch the structure on it too much as well. So that's rounding it using maybe the Wilmore flow, something making things rounder, and preserve the conformal structure. Again, how to measure angles on the surface so that it's not stretched. The last one is also a minimal shape, our blood cells, for example, but it minimizes the bending energy, not the surface area, with fixed and closed volume. And those things are isoperimetric ratio because it's kind of scale invariant. So those are how our blood cells are constructed. And understanding surface theory helps to understand biology here and how our blood flows through our veins. So as I said, I want to go into minimal surfaces in R3 here. And this one here is a typical minimal surface. These are pictures I made in Hanover when we were doing exhibitions, and we really had soap and some toys and we put it into water, that's what you see. So this is a piece of typical minimal surface, which has this saddle structure. So in two directions, it would bend in different directions. Very important negative Gaussian curvature, that means. So a question to our audience here. What you see is very smooth. Do you think if you have a random minimal surface with a certain boundary, should the minimal surface be smooth or should it have singularities? So maybe hand raise for those who think that this minimal surface should be smooth. Smooth?
Can we see some hands? High up, please.
High up, please. Smooth? Should have singularities?
Singularities.
No singularities? Well, I should maybe define singularities first. Okay. So this is another minimal surface you can do using soap film. And you can see there are clean edges, like a pentagon here inside, which shows that it doesn't need to be smooth, although, well, it's just the boundary is not smooth anyway, but it's inside completely without boundary. And still you see a pentagon in here. Okay?
It's not C1.
Yeah. So next picture, if you take a cube and put it into soap film, that's a picture you would see. Okay? Well, we saw the previous picture before. That was probably with some enclosed volume in the middle, but it doesn't count. But a question to the audience again, do you expect the solution here to be unique? So when you put boundary, some cable, whatever, into soap, pull it out, do you expect the same soap film every time you pull it out? Yes? Raise your hands. No? Okay, it's on the no side, which is true because if you just take the picture from the other side of the cube, you would see the right-hand picture. Okay, so you have a symmetric boundary but a non-symmetric surface, meaning it cannot be unique. And actually, if you do the real experiment, if you are on the right-hand side, you can take a little blow into this ridge here, and you would jump to the other solution. You should try it out. So this is my colleague, Markus Röser in Hanover at that time. We were at this exhibition, and he was so proud because it took many, many attempts to get this dodecahedron inside the dodecahedron picture. We probably tried the whole day. And you can see here also that you have this crystal picture films inside this one here. And if you're interested in doing that at home, I would suggest to do so. And here we have the best recipe for soap solutions to do so. So you need baby shampoo, which the purpose for it is it doesn't burn in your eyes. Then it's good for soap film. Then you need enough sugar so that it doesn't pop too early. Little toothpaste for the glycerin, so that's a little thick. And of course, water. Okay, so if you want to try, do it. But the problem in China to get proper kids' toys that does these figures is slightly difficult because you want to do any figure you want and not just the prescribed one, which is a little difficult sometimes to get in China. Okay, so that was R3. We saw little pictures. Let's see more pictures, what happens when the minimal surface is in the round sphere instead. So there are not that many compact examples, so without any boundary. The most famous ones are the Lawson surfaces from the 70s. And well, you have the geodesic sphere. You have the very famous Clifford torus, which, by the way, is the only embedded minimal torus in S3. This one is of genus 2. Well, it has 3 holes and 3 legs, but it's a genus 2. If you just put the middle leg put it into this shape here, it would have 2 holes. Okay. This one is conjectured to be the only embedded minimal surface in S3, but no one knows. Genus 2. And for higher genera, we know it's not true. So this is the Lawson surface again of genus 3, which have just one more leg than this, but it's a different stereographic projection to R3. That's why it looks slightly different. And this one has genus 4, but in contrast to these ones here, we have a layer in between. So you can add the layers here between the leg and add the number of legs, which are basically the numbers K and L, and K times L is the genus. Okay? what does it have to do with soap film? Let's have a picture. So what happens is if you are in the round 3 sphere, you would project your geodesic 2 sphere to R3, or everything actually to R3, but the geodesic 2 sphere mapped to S2 in R3. Now, we have a circle on there, and the z-axis, and we basically, on these lines, of these 2 lines, we define points that are equidistant to each other. So 2k plus 2 points on this circle, geodesic in S3, 2l plus 2 points on the geodesic in S3, which project to the z-axis, connect the neighboring ones together, and we get a wireframe. And this wireframe, we can dip into soap and get the solution, which is a soap film, okay, or the solution to the plateau problem in S3. Now, Lawson's idea was to rotate this thing and reflect the thing to get a compact surface. Because that's hard to explain, let me show you a video. So this is my plateau solution. I rotate the thing along the red line, which is just a rotation in S3. And I change the line to the other edge, rotate again, and rotate. And I now take a different stereographic projection just to obtain my original shape that's our most symmetric. So the last deformations here are just different stereographic projections from S3 to R3. Okay? And as you can see, if I change the angles on top and bottom of my foreground here, I would need more pieces to rotate this last piece here. So I get more handles. That's why more genus is created. Okay? So this is the Lawson surface. And the cool thing about geometry generally is that we don't fix what we use to prove our theorems or to understand our shapes. Because it's minimal surface, so we want to have optimal shapes. We do use a lot of geometric analysis. Well, other people use geometric measure theory as well, not necessarily me, because we are interested in conformal structures, meaning that should be angle preserving. We have a rotation by 90 degrees, which gives you a complex structure. So complex analysis and Riemann surface theory come into play, okay? And the PDE, underlying minimal surfaces or Wimel surfaces, are integrable in the sense of integrable systems. So you have the connection to algebraic geometry, spectral curves, integrable hierarchies, okay? And underlying the construction of the Lawson surfaces are these rotations and reflections, which correspond to tilings, actually, of S3. And if you have a different tiling and different setup, and you find different minimal surfaces in the fundamental piece, basically, which intersect the boundary orthogonally, you can just reflect it on the boundary and get your compact surface back. So there are a little bit of combinatorics come into play. So, for example, I would be interested whether this Einstein tile, right, whether we can find a minimal surface that has the structure of the Einstein tiling of R2. And if you compute the area of these Lawson surfaces I showed you for very large genus, we can actually also, well, I had to learn a bit of number theory to actually find the coefficients, which I found very exciting. So generally, thank you for the opportunity to do a little propaganda about my work, but I think I want to show that, first of all, it's pretty because you have all these pretty pictures to show, but second, every day you have to learn something else to solve very traditional problems that is very easy to explain. Thank you.
Thank you for a really cool talk, the cool videos there. Okay, so do we have any questions for Professor Lin? Yes, I see a hand in the middle right there, waving.
May I ask 2 questions?
One at a time, please.
Okay. There's a classical result says that for embedded minimal surfaces with finite topology in R3, the Gauss curvature decays in the rate of like 1/r². So I wonder if there are extensions to this result. For example, we replace R3 to other non-compact 3 manifolds or even higher dimensional manifolds?
Well, I would say ask Professor Yao on this.
Maybe we'll save that for later then. What's your second question? Oh, there's a question over here. Maybe is that? Maybe we should give others a chance.
Does there exist a wireframe that offers such a minimal surface that is, say, composed of infinitely many smooth pieces? Just like the cube example, but more complicated.
I mean, it depends on what if you put many together, you can definitely get more, right?
Oh, yeah.
Sure, but I'm not sure whether so for example, the Shirk surfaces are obtained by a piece of the Shirk surface is obtained if you take two wedges next to each other and you would, extend that particular surface. So Shirk surface, basically you take two planes intersecting orthogonally or not orthogonally, it doesn't matter, and you add holes in the middle so it becomes non-singular.
Okay.
That one is kind of a boundary value problem if you take two just wedges with distance 1. But of course, you don't see the whole surface at once. You just see a piece of it. But it's real analytic kind of, these kind of things set up. And if you just extend it, you would see the whole Shirk surface. But I think as a boundary value problem, you don't see all the genus.
Okay.
If you really want one boundary and just a lot of genus in between, I'm not sure. But on the other way to do it is actually to take the boundary of a Möbius band, for example. You can put that into SOAP, and there are two different solutions. One which is basically disk type, but then you can destroy the middle to get a Möbius band. And that way you can see a little bit of topology as well. But I don't know whether you can, without enforcing the frame, that you can get a real torus or genus. I haven't seen that. I would be interested to see that. I would need to do some experiments on this.
Okay, I think we're maybe running out of time here. So let us thank Professor Lin once again for a beautiful talk.